Hello everyone, and thanks for watching Edupedia World videos. So in this session of chemical equilibrium, we will look at properties of K equilibrium. Okay. So we will only look at the mathematical properties, as in what happens to the value of K equilibrium if I make some changes to my chemical equation. Okay. So basically what we will be doing is we will be applying various algebraic operations on the chemical equation. So we already know that a chemical reaction can be treated as a mathematical equation in some ways. Okay, with reactants as your left hand side and products as your right hand side. Okay, so just like in a mathematical equation, I have LHS equals to RHS. Okay, in a chemical reaction, I have reactants giving you products reversibly over here. Alright, so now just like we apply mathematical operations on this mathematical equation, we will apply mathematical operations, algebraic operations on our chemical reaction. So some of those are, we'll look at what happens to the value of K equilibrium upon addition of two reactions. Similarly, what happens upon subtraction. What happens if I multiply my reaction, the whole reaction, that is both sides, with a constant factor. And what happens if I reverse the reaction, that is if I write product to reactants instead of reactant to product. Okay, so let's look at them one by one. Let's start with what happens upon reversing a chemical reaction. So see, if I have any given chemical reaction, let's say I have PCl5 going to PCl3 plus Cl2. So this is one way of writing this reaction, okay, where PCl5 is your reactant and is written on left hand side. Okay, and I know that chemical equilibrium constant, okay, equilibrium constant for this is given as K1, right? So what happens if instead of writing the reaction in this way, I write the same reaction in this way? Okay, ultimately it is a reversible reaction. Okay, so even my products are reacting to form the reactant back. So what happens if I write the initial products on the left hand side now? So now these have become our reactants and this is our product on the right hand side. So that is what happens if I write left hand side constituents on the right hand side and the right hand side constituents on the left hand side. So if this is my new K equilibrium K2, can I say that K2 has some relation with K1? So let's find that out. Okay, the algebraic operation, okay, whenever the algebraic operation involves reversing of chemical reaction, the equilibrium constant of the new reaction is reciprocal of the original equilibrium constant. That is, the law here says that K2 will simply be equal to 1 by K1. Okay, that is whenever you write your chemical reaction in the reversed order, alright, then K2 becomes equal to 1 by K1, that is your equilibrium constant, okay, will be the reciprocal of the old or original equilibrium constant. Alright, so see here, ultimately equilibrium can be established from either direction. That means I can start from reactants or products. What's important is the way of writing. Okay, so here the only difference in the two reactions, okay, K1 and K2, is the way of writing. Okay, I have written PCl5 on left hand side here and here I have written it on right hand side. The reaction, the experimental conditions, the container will all be same. Okay, so nothing else is changing, only the way of writing. So why is it that equilibrium constant gets, you have to take the reciprocal of equilibrium constant? It is because K2 is what? PCl5 divided by concentration of PCl3 and concentration of Cl2. Okay, and we already know that K1 is given to us and it is simply equal to concentration of PCl3 into concentration of Cl2 divided by concentration of PCl5. Okay, so it's simple. Okay, you can simply observe that K2 is nothing but 1 by K1. Okay, by looking at the expression of K1 and K2, we can simply deduce that this law is quite true. Now let's see what happens if I change the stoichiometry of my chemical reaction. So how do I change the stoichiometry? Okay. Let's say I have initial reaction as capital A and capital B reversibly forming the products capital C and capital D. Okay. The balancing gives stoichiometry as small a, b, c and small d. Right. So this is my original reaction with equilibrium constant K1. Now how can I change the stoichiometry? I can change the stoichiometry by multiplying with the same factor, say n, on both sides of my chemical reaction. So n can be any number. It can be a whole number, it can be a fraction. Okay, it cannot be negative. Let's not take it as negative number, but on any positive number. Okay, so that's how I can change stoichiometry. Just like in mathematical equation, I can multiply or divide by any factor on both sides of my equation. So the same thing I can do over here for the chemical reaction. Let's say the factor is n. Okay, so the new stoichiometry becomes small na, small nb, okay, and nc and small nd. So this is how my new chemical reaction looks like. Let's say its equilibrium constant is K2. So law says that K2 will simply be equal to K1 raised to power n. Okay, so this is what you have to memorize, that whenever the chemical reaction is multiplied by a common factor on both sides, the equilibrium constant, okay, of the new reaction is simply equals to equilibrium constant of the original reaction raised to power n. So let's observe what happens, or how can I prove this. So it's pretty simple. Okay, K1 is what we can write as capital C to the power C. Okay, concentration of D at equilibrium to T. Similarly, concentration of A at equilibrium raised to power small a, and concentration of B at equilibrium raised to power small b. What about K2? Okay, so K2 can be written as concentration of C raised to NC, concentration of D raised to ND, divided by concentration of A raised to Na, and concentration of B at equilibrium raised to Nb. Okay. So I can write this whole thing, okay, by simple rearrangement. Okay, using simple mathematics, I can say that this expression is nothing but it looks like this. Okay, this, and the whole thing is raised to the power small n. Right, and what is this? This is simply equal to your K1 over here. Okay, it is simply equal to the value of K1. That means K2. Okay, K2 is nothing but equal to K1 raised to power small n. Okay, so this is how you can change the stoichiometry and find out the corresponding change in equilibrium constant. So just remember that n can be any value. For example, it can be 3, or n can be say 5 by 4. Alright, but whatever that value is, okay, it has to be multiplied on both sides of the chemical equation simultaneously. Alright, now what happens if I add two chemical reactions? Let's say my initial, okay, my original reaction is capital A going to capital B, and the balancing looks like this: small n, small b are the stoichiometry, and the equilibrium constant is K1. So I know that K1 is equal to capital B divided by capital A raised to their stoichiometric coefficients, and my other reaction is this. Okay, and its equilibrium constant K2 is also given to me. Okay, and it is given as this, right? Okay, so this we know how to calculate. The question is, what happens if I add chemical reaction 1 and chemical reaction 2? Okay, so first we need to find out the result of addition. Okay, so if I add these two reactions, what will I get? I will get 1 plus 2. Okay, so if I do this, I'll get this. Okay, so this is going to be my resultant reaction. Okay, so first you should be able to identify this resultant reaction. Now we need to identify the value of its equilibrium constant in terms of K1 and K2. Okay. So the law says that whenever two chemical reactions are added, their equilibrium constants get multiplied. That is, it says that if this is my resultant reaction on addition of reaction 1 and 2, then K3 will simply be equal to K1 multiplied with K2. Okay, so this is what you have to memorize, that K3 is simply going to be equal to K1 into K2. How is that? So it's pretty simple again. So K3 can be written as concentration of B raised to small b concentration of D at equilibrium. Similarly, concentrations of C, A raised to their stoichiometric coefficient. So I can separate this whole thing out, okay, in two sets. Say one is this, okay, and the other section is this. Okay, all right. So now it's pretty clear that this is what, this is nothing but your K1 from over here, and this thing here, this is nothing but your K2 from here. So K3 is nothing but, it is equal to K1 multiplied with K2. Alright, and this is how you calculate your equilibrium constant of the resultant chemical reaction. Now lastly, let's look at what happens if I subtract two reactions. So now once again, let's assume the same reactions, A, okay, to B and C to D. Okay, so their equilibrium constants are again given to you, say K1. Alright, and we know how to calculate K1. Okay, and K2 is also given to you, and we also know how to calculate K2. What we need to do is, now we need to subtract equation 2 from equation 1. That is, I want to find out the resultant equation when I subtract 2 from 1. 1 minus 2 will give me A minus C with its stoichiometric coefficient and B minus D. But this is not your resultant equation. You haven't yet obtained the resultant chemical reaction. Okay, because chemical reactions don't have negative signs in them, right? They have only positive signs. So how can I bring positive over here instead of negative? Once again, chemical reactions can be treated as mathematical equations. So that means I can simply take this negative sign with D over here, and that will make it positive. Okay, similarly minus C from here will go on this side and become plus C. So that means this chemical reaction can be rearranged to give me my resultant chemical reaction, okay, in this form. And see that the resultant chemical reaction is also balanced, okay, with stoichiometric coefficient small a, small d, small b, small c. That is, the respective stoichiometric coefficients haven't changed. So now since we have found out what is the resultant chemical reaction, we need to find out the value of K3, the resultant equilibrium constant. So how can I calculate K3 in terms of K1 and K2? The law says that K3 is going to be nothing but reciprocal, or to say quotient, okay, or to say the quotient of K1 by K2. Okay, so this is going to be my resultant value of equilibrium constant, or the equilibrium constant for my resultant chemical reaction. Okay, K3 is equal to K1 by K2. This is what you have to memorize. Okay, whichever is subtracted, that equilibrium constant comes in the denominator. Okay, and the reaction from which you are subtracting, that is 1 over here, comes in the numerator. So how is that? So K3 can simply be written by observing this resultant equation, okay, as B into C divided by D into A. raised to their stoichiometric coefficients. Once again, rearranging the whole thing, okay, we can rearrange this thing and we can write b by a, alright, divided by d by c. Okay, so simple mathematics, we can simply observe this equation and write it in this form. Alright, and what is your numerator now? B by a, which is simply equal to the k1 over here. And what is your denominator? D by c, which is simply equal to k2 over here. So k3 is nothing but k1 divided by k2. This is how you calculate the equilibrium constant for resultant chemical reaction, which is obtained by subtracting two given chemical reactions. Okay, so these four algebraic operations are all you need to know. Okay, and this is all you need to know about mathematical properties of equilibrium constant. In the next session, you will look at some of the numerical examples in which we will utilize these formulas which we just studied, the four formulae. Okay, and then subsequently we'll start with new topic. So until then, and once again, thanks for watching Edupedia World videos.